Good evening everybody. So, today we will talk about some other type of distortion which we will consider as Jahn-Teller effect. So, for the two types of distortions what we have seen so far, which are basically tetragonal type, and if we consider in an octahedral geometry, that considering the z axis, which is either elongated or compressed. So, we will have elongation as well as compression. So, in these two cases what we see that depending upon the amount of distortion in a particular direction, that means the z axis, if we have the elongation as well as the compression in another case, we will definitely get different electronic configurations. So, the electronic configurations here also, the electronic configurations for both these two cases would be different, and this basically results from a corresponding distortion over there. So, this Jahn-Teller effect, what we will see that depending upon the electronic configuration for some systems, say D4 or D5 system, we will get a lower energy situation where the distortion is automatically coming into the system or the molecule or the ion. So, what we will see that in this particular Jahn-Teller effect, the geometrical distortion of molecules or ions that is related with certain electronic configurations. So, if we now focus our attention on the electronic configurations, and those electronic configurations would be related to the reverse one, that means the distortions. So, how the different electronic configurations which are known as the corresponding electronic configurations which would be Jahn-Teller sensitive. So, Jahn-Teller sensitive electronic configurations will give rise to certain amount of distortion within the molecules. So, we get certain elongated or compressed situation for this effect. So, we have in octahedral symmetry what we have seen that we can have the T2g and Eg set of orbitals. They are splitted already in a particular octahedral symmetry. So, if they are present in nonlinear polyatomic molecule and if they are degenerate, that means within the T2g set we have the dxy, dxz and dyz orbitals, and in the Eg set we have the dx square minus y square and gz square orbitals. That means one is the triplet state, another is the doublet one, and here 3 orbitals are degenerate, and in this particular case we have 2 orbitals which are degenerate. So, the degeneracy is determined by distorting the molecular structure to attain low symmetry or thus low energy situation. So, this distortion will cause or will just lift all this particular degeneracy, that means they will no longer be degenerate, that means T2g set will have further splitting and the Eg set will have further splitting, and unequal occupancy of those splitted level will give rise to a low energy situation, and as a result we have the splitting, and the splitting we know that originating from the lower symmetry from the octahedral symmetry. So, if we have a corresponding hexa-aco copper ion, because we are talking this in terms of the corresponding 3D9 ion, and the 3D9 system is Jahn-Teller sensitive. So, when we have a typical octahedral geometry, because we are not restricting anything, only the 6 water molecules are surrounding the copper 2 ion. But in this particular situation, we will find that the molecule which is nonlinear polyatomic molecule and the two degenerate sets, the T2G set and EG set, will undergo corresponding splitting. And as a result, we have a corresponding elongated situation. The figure, the molecular structure of this system tells us that along the z axis we have two longer copper oxygen bonds compared to the equatorial 4 copper oxygen bonds. Therefore, we have the two axial copper oxygen distances which are 2.38 angstrom. That means these are comparatively longer corresponding to the 4 equatorial one. These 4 equatorial copper oxygen distances are in the range of 1.95 angstrom. Therefore, we have a tetragonally elongated situation due to unequal occupancy of the EG level. So, we have 2 electron in one particular level and 1 electron in the other level. So, that is why it gives rise to the corresponding elongated situation. So, we have this is the elongation, this is the elongation axis along the z axis. So, it is basically compared to the octahedral situation is a z out situation. So, d orbitals with z component are stabilized. So, since we have the longer distance of copper oxygen for this, we get the corresponding situation where we have the corresponding splitting basically. That means these two levels, one orbital and the other orbital. So, this z out is the z component is stabilized, that means this is dz square orbital and this is dx square minus y square. So, in that particular situation and the lower end also we have two orbitals in the lower end where we have the z components, that means the xz and yz. That means xz and yz orbitals are stabilized since they have the z components and since we are doing something where z component is stabilized, and this is therefore the xy. So, the amount of stabilization for this particular electronic configuration for copper 2 plus is due to the corresponding occupancy for 2 electrons in these two levels and 1 electron in this particular level. So, unequal occupancy in the EG level which are not half filled or full filled, which is partially filled. So, will give rise to the corresponding stabilization of minus half delta 1. So, this particular one which is facing the ligands directly will have higher amount of splitting, that is why it is the corresponding splitting is delta 1. So, this is delta 1 splitting and this is delta 2 splitting, and we call this splitting from the T2G and EG set in an octahedral geometry is due to the corresponding Jahn-Teller distortion. So, this distortion further gives rise to the other situation, that means where we have the tetragonally compressed situation where the z component are destabilized, which is very much similar to that what we have observed in case of the corresponding tetragonally elongated and tetragonally compressed situation. So, this is basically equivalent to the tetragonally compressed situation where these two orbitals, the z component would be destabilized. That means this would be the dz square orbital and this is the dx square minus y square orbital. So, we can have, when we have the 3d9 electronic configuration, what we see that we have the 4 levels, that means the T2G level which are filled, and after splitting also they all are filled, and in the EG set we can have two situations, that means whether it is 1 electron in the dz square level and 1 electron in the dx square minus y square level. So, these are the two situations where z component is stabilized. Basically, z is the lower energy, so dx square minus y square is the higher energy. So, dx square minus y square one configuration would be for z out situation. So, this is for z out situation and this is for z in situation, and which is very much similar to that of the corresponding tetragonally elongated and tetragonally compressed octahedral distortions. So, this particular case also the occupancy in the z square level and the occupancy in the x square minus y square level further can also be clarified if we go for the corresponding spectroscopic technique. So, electron paramagnetic resonance is one such technique where we can measure the corresponding electronic paramagnetic resonance spectrum for the copper ion. So, in these two cases we can have two different types of spectrum for clear identification of the situation where the electronic configuration is dz square 1 or dx square minus y square 1. So, this is basically the corresponding one for the compressed situation, and for other situations where we can have K2CuF4, the tetrafluorocopper salt, potassium tetrafluorocuprate, which is potassium tetrafluorocuprate and sodium tetrafluorocuprate. So, interestingly within the crystal lattice basically these molecules are showing CuF4 and CuF4 situation, but due to the different types of crystal packing in this particular situation. So, this CuF4 and this CuF4 also interact with other fluorine atoms from the adjacent molecules, such that this copper center would be octahedral CuF6. So, 4 from the same molecule, that means the same copper environment, and 2 is basically 2 other fluorine atoms are being shared from the upper side and the lower side in the crystal lattice. So, this is basically the most compressed one where we have the potassium is in the crystal lattice also, which is Z in situation, and when we take the corresponding sodium salt, it is basically the Z out situation. Similarly, for Cr2F6 also we have the corresponding chromium 2, and this particular chromium 2 is in the high spin D4 situation, which is also very much relevant for the Z out situation, and we have the sharing for the corresponding chromium around the 4 fluorine atoms. So, this particular one shared from the adjacent molecule. So, we have all these examples for this typical situation for this distortion. So, what we see that in case of copper, which is also the copper in hexa-aco molecule, that 9 electrons what we can have, these 9 electrons are there. So, this particular one, so this copper 2 in regular octahedral geometry, this here there will be one more electron here. So, we can have 6 plus 3 9 electrons over there. So, this is paired and this is the unpaired one. So, when they are doublet and they are degenerate, we do not know which one is dx square minus y square and which one is dz square, but after splitting we can clearly identify the corresponding number of electrons, since it is a corresponding situation where we have the elongation. So, increasing bond length of the octahedron, that means the corresponding distortion along the z axis. So, z components are stabilized, dz square would be stabilized and dxz and yz are also stabilized. So, we have the single unpaired electron in dx square minus y square. So, that is the corresponding situation what we have seen in case of z out. So, what happens if we go for the bidentate ligand? So, when we have the bidentate ligand like this, that means if we have the corresponding bis ethylene diamine copper diaco molecule, so where we have the two corresponding water molecules are there which are in elongated direction. So, long axial copper oxygen bonds what we have seen in case of hexa-aco molecule also. So, it is in range of 260 picometer or 2.60 angstrom, and the short in plane copper nitrogen bonds are in the range of 2.03 angstrom. So, they are shorter in plane, these copper nitrogen bonds are shorter, and we have the corresponding longer distances along this particular axis, which is the corresponding elongated axis, and we have the bis ethylene diamine molecule for this sort of distortion. So, when we have the chelate rings also we see the distortion, because the chelates are only restricted within the plane which is the corresponding square plane, and the axial directions are free for water coordination. But this is also true when we have the corresponding copper tris ethylene diamine molecule. So, in octahedral geometry, when we have the tris ethylene diamine copper molecule, that means 6 copper nitrogen bonds can be formed from the binding of one chelate, then the second chelate and the third chelate, which has a 2 positive charge. So, what we see that this particular one, if we find that if this particular direction, again we will consider this particular one, that means the situation is Z out situation. So, these two axes, that means the Z axis, will try to elongate, that means these two copper nitrogen bonds will be longer compared to other 4. So, when this particular bond will try to be longer compared to this bond, that means within the chelate ring, this is the copper position. So, we can have this copper nitrogen bond is longer compared to this copper nitrogen. So, which can be nicely compared if we just go for the in plane short bonds for this bidentate ethylene diamine ligand, because here 2 copper nitrogen bonds are in the square plane. So, these 2 bonds will be shorter, but the situation for these 2 ligands are different. We have one long bond and one short bond, similarly one long bond and one short bond. So, as a result, this particular chelate ring will be distorted towards this side and this particular one will be distorted towards this side. That means, we can have corresponding, this bond will go towards this side and this bond will also go towards this side, because it is already chelated, it is not free like free water coordination. So, due to that, basically is this particular one, that means this nitrogen copper nitrogen axis, the nitrogen copper nitrogen axis. So, ideally if we do not have any distortion related to this lengthening of this nitrogen in the tris chelate molecule, what we see that this is close to 180 degree, but when we just move from this right hand side direction and this is also moving towards this square plane, we have something where we get a corresponding nitrogen copper nitrogen axial. So, this is axial and this is also axial. So, nitrogen axial, copper and nitrogen axial angle should then be less than 180 degree. So, here we see that this is the corresponding long axial copper nitrogen bonds, which are much more than what we have seen just now for the ACO copper molecule, which was 2.60 angstrom, but it would be 2.70 angstrom. And also the short in plane copper nitrogen bonds, which were below 2 angstrom in the ACO molecule, but it is above 2 angstrom, it is 2.07 angstrom. And this particular picture clearly shows that this particular direction is moving towards on the right hand side, and this is also moving towards this direction, towards the chelate ring direction. As a result, we have this nitrogen copper nitrogen angle less than 180 degree. So, we see also for the tris chelate molecule for copper, we still have the corresponding distortions related to the Jahn-Teller distortion. So, what we see that for the different d electrons starting from the D1 system to D10 system, and we have two situations. One, we already know that for the octahedral complex, the geometry, if the geometry is the octahedral one, we have the situations like the high spin situation and the low spin situation. And just now we are discussing about the D4 system, and this is the corresponding copper. So, in the copper case, which is not related to its high spin and low spin electronic configuration, it has only one electronic configuration, which is purely the corresponding 3d9 electronic configuration, and we have in both these two cases it is correspondingly it is giving strong Jahn-Teller effect. So, this strong Jahn-Teller effect for 3d9 system is therefore expected because Eg which is unevenly occupied. So, the Eg level now in case of copper 2 plus we have 3 electrons, and those 3 electrons should be unevenly occupied for this Eg level, and that is why we get that the Eg level will undergo the corresponding distortion, which is the corresponding Chetty distortion. So, where the entries are not there, we do not have any Jahn-Teller effect expected for there, and for other cases that means we have the corresponding low spin D7, low spin 3D7 system which is Cobalt 2. So, Cobalt 2 also can give rise to strong Jahn-Teller effect and the high spin D4 system. So, these are the cases. So, 3D9, 3D7 and 3D4 situation we can have the corresponding strong Jahn-Teller effect. But what is our weak Jahn-Teller effect? The weak Jahn-Teller effect is due to the uneven occupancy in the T2G level, which is not facing the ligand directly, because we all know now that in octahedral geometry the Eg orbitals are facing the corresponding ligands directly along the 3 Cartesian axes x, y and z. But in case of T2G the electrons are there, but these orbitals are in between the Cartesian axis, such as if we have the dxy orbital which is between the x and y axis and which is in between and which is not repelling the ligand electron density much more. So, whatever Jahn-Teller effect we can see due to the uneven occupancy in these levels, that means when we have 1 electron in the T2G level, 2 electron in the T2G level, or here also after fulfilling this one, that means the 5 electrons smeared out for all levels, then the 6th electron and the 7th electron is coming in again into the T2G level. So, these all will basically giving a very weak Jahn-Teller effect for these situations. So, we can get some effect, we can get some distortion, and some of these effects are stronger what we see in case of the copper. The most renowned example is the copper 2 plus, but in other cases the distortion is very less, and that also can be observed due to the different electronic transitions in optical spectroscopy also. So, we can also have some idea about the corresponding effect due to the distortion. So, the thermodynamic effect that we will see also afterwards, that the binding of ethylene diamine to all these molecules starting from the main group element, the calcium, to scandium, titanium, vanadium, chromium, manganese. So, these are the things that where we can have the corresponding double humped curve we can get. So, these double humped curves are also very much useful for the corresponding metal oxygen bond in the solid state that we will discuss afterwards. Similarly, for the different aqua molecules we can have the corresponding hydration energy, and hydration energy also follow similar double humped curve, where we see that some amount of crystal field stabilization which is operating as we move from D1, D2, D3 to D4 situation, and there also as we move up to this particular D8 or D9 situation, there is a gain in the crystal field stabilization energy, and due to that gain we basically get some extra stabilization due to the corresponding gain through crystal field effect. So, here basically for this log K1 En is a function of number of d electrons. So, the corresponding binding constant for one ethylene diamine binding can be monitored depending upon the number of d electrons present. So, it is moving as we move from calcium to manganese to zinc, it is basically rising, and is due to the rising baseline is due to the ionic contraction, because the more number of protons and electrons are there. So, higher nuclear charge will basically go for ionic contraction and size is less, and we can have some higher values for these K log Ki values. Now, in this particular case also we see some amount of stabilization in case of copper, which is above this dotted line, which is due to the corresponding crystal field stabilization energy in 3D9 situation. So, there is a gain in energy for due to crystal field splitting, and that gain in corresponding energy for crystal field splitting is reflected, and our log K1 value can go from here the dotted line to up to this point. But experimentally what we get, experimentally this value is much more, it is close to 10, and this increase in these values from say 6 to 10 is due to the corresponding Jahn-Teller distortion. So, the stabilization what we get is experimentally that can be verified if we determine the corresponding log K1 value for the binding of ethylene diamine to the copper center is due to the corresponding extra stabilization for the Jahn-Teller distortion. So, we get this much amount of stabilization. So, the situation for copper 2 in 3D9 electronic configuration is that it is the most stable situation after distortion. Similarly, in case of 3D4 situation, what we also know that it has also stabilization due to Jahn-Teller effect, and that basically gives us some amount of stabilization, and we have a double hump curve therefore, where the peak is here for 3D4 and the second peak is at 3D9 due to copper 2. So, any kind of physical information what we get due to that Jahn-Teller stabilization is reflected from determining the log K1 values for ethylene diamine coordination or binding. Next, we will just move on to another situation what we just discussing for the corresponding spin state. So, whenever we have any d electron configuration, say 3D, 4 or 5 or 6 or 7, we see that in case of 3D5 we can have two electronic configurations in octahedral field. So, the field is octahedral. So, we have the corresponding high spin configuration and the low spin configuration. And in case of 3D6 we have determined earlier that for 3D6 the energy for the high spin situation and the corresponding energy for the low spin situations can be determined nicely if we know the corresponding amount of splitting. So, this have two different types of configurations. One is that corresponding T2G4 EG2, and in case of this low spin it is T2G6, and these two situations can very nicely be handled if we determine the corresponding values for the high spin and the low spin configuration. So, in this particular case it is 2/5 of delta O plus P, and in this case it is minus 12/5 of delta O plus 3P, because we have 3 electron pairing. So, in this particular situation if we just consider that 3D6 we have a high spin configuration, and in high spin configuration we know that delta O is less than P or P is greater than delta O. Now, if we consider that P, since P is greater than delta, therefore, if we can consider the P is equal to delta plus x delta. So, if we put these values for these, what we find that in case of E high spin, the energy for this would be 2/5 delta plus x delta which will be equal to 3/5 delta plus x delta. Similarly, we also can put for energy for the low spin. So, it will be minus 12 by 5 delta plus 3 delta plus 3 x delta is equal to 3 by 5 delta plus 3 x delta. So, what we see now that both the two values can now be compared by looking at the corresponding delta x values. So, this low spin will have 3/5 delta plus 3 x delta and the high spin has 3/5 delta plus x delta. So, this will have, therefore, we can consider it is as greater energy. Since it has greater energy, that means we get the situation as the corresponding high spin state. So, 3d6 will result high spin state. So, if the condition is that delta O is less than P, we have the corresponding high spin state definitely. So, now we will see that for situations like the corresponding configurations, it can be for 4D and 5D as well. For D4, D5, D6 and D7, if we see that there is always a balance between the corresponding crystal field energy and the pairing energy. So, if there is a critical crystal field, so at the critical crystal field we find that delta is equal to P. That means this is at somewhere where we can consider is at a crossover region. That means we are moving from one direction to the other such that if on the left hand side the low spin state is of low energy, on the right hand side it would be of higher energy. So, at this critical crystal field we find that below this critical field and above this critical field we have two situations, and these situations are considered in such a way that below the critical field we have, if we have the high spin state is of low energy, and above this critical crystal field the low spin state will have low energy. So, at this particular point we can have a crossover, and this particular crossover region can be found out where delta is close to P and which is in the range of thermal energy, that means kT. In the range of thermal energy, which is nothing but kT. So, how we get this thermal energy to change over from one particular form to the other, that we will find in case of the spin crossover. So, this spin crossover situation we have, see that this can be abbreviated as SCO. It is a phenomenon that occurs in some metal complexes. Not all metal complexes will give the spin crossover situation, wherein the spin state of the complex changes due to external stimuli such as variation of temperature, pressure, light irradiation or an influence of magnetic field. That means we are we are giving some external stimuli as temperature, pressure, light irradiation or magnetic field. So, once we change the corresponding temperature, and as we have seen just now that it is in the range of corresponding thermal energy, that means the kT, that means the kT can control the corresponding spin state of the molecule. So, there are some beautiful examples for all these molecules where we will find that this particular situation can be handled nicely by finding out the right ligand system and the right metal ion. So, we have this particular one. So, thermal energy can control this particular situation where we can have this high spin state can go to the low spin state which is of low energy. That means this delta is basically now close to the corresponding pairing energy, and as a result we push these two electrons to the lower level for pairing. So, if they are close to this P, the P is close to this delta value, we do not know what should be the situation, whether it would be high spin or whether it would be low spin. So, there are several techniques also how we can find it out, the corresponding spin crossover or spin crossover molecules that can be used to detect the SCO phenomena in metal complexes. So, there are right number of these techniques which can be applied to find out the corresponding spin crossover situation for these molecules. And when we find that spin crossover for several iron compounds can be observed if the ligand field strength is such that the difference between the lowest vibronic energy levels of the high spin state, which is 5 T2, is the corresponding spectroscopic term related to the occupancy in the T2G and EG level. So, we find there that the corresponding state of 5 T2 and the low spin state which is 1 A1, because it has 5 spin multiplicity value and here the spin multiplicity value is 1. So, it has high spin value. So, this particular value which is 2s plus 1. So, it has 2 unpaired electrons for this s value, and we have this corresponding value for this, that means the 4 unpaired electron is there, the capital S value is equal to 2. So, we have this particular situation and this is the low spin state, and these two states are comparable with thermal energy kT, which is kBT. kBT is nothing but the corresponding constant named after Boltzmann. So, is abbreviated as capital B also, K small k abbreviated with subscript capital B gives the corresponding Boltzmann constant. So, these two states when they mix up and when one is of low energy than the other, we can change the corresponding situation from one state to the other. Then the spin transition behavior can be influenced by chemical alternation. We all know that the ligand replacement, the change of non-coordinating anion, the solvent molecule, substitution of spin state changing metal ion by another metal ion. So, these are the things what we can use to control the corresponding spin transition, whether we will be getting the corresponding high spin molecule or the low spin molecule. So, if we change the ligand system, the same iron 2, if we are restricting our attention on iron 2 compound itself. So, if we change the ligand system, the iron 2 can give rise to the low spin compound as well as the high spin compound depending upon the nature of the ligand. Then we can go for the change of non-coordinating anion, which is outside the coordination sphere, which is not coordinating the metal ion, but which is influencing the corresponding crystal field for the crystal lattice, and it can also affect the corresponding spin behavior. Then the solvent of crystallization, and sometimes the substitution of the spin state is possible if we change the metal ion, the iron 2 by some other metal ion. So, it can also be influenced by the physical perturbation what we have seen just now, that irradiation of light, application of pressure and magnetic field apart from temperature. So, apart from temperature, three other physical perturbation can be applied to see the spin state transition, which are the light, the pressure and the magnetic field. So, the situation what we can get for the spin crossover compounds, which is a iron 2 compound, which is a 3d6 electronic configuration. When it is low spin, where spin is equal to 0, which is a diamagnetic state, and when we move from there, that means these two are in equilibrium from temperature, pressure or the light. So, these are the things which can give rise to the corresponding transition. So, we get the high spin state, that means two of these paired electron can move to the upper state, where we get 4 unpaired electron. That is why we have the spin multiplicity 5 due to S value equal to 2. So, S value 2 gives rise to the corresponding spin multiplicity equal to 5, and we can monitor these by changing the temperature from this. So, you just go from there to, then we move to the corresponding spin value, that means when it is diamagnetic, which is 0, and we can have the corresponding maximum paramagnetism which is close to 1, then is going to this particular pathway and it is basically going for the paramagnetic situation. Then again if we cool down, it is taking a different pathway, it is not the same pathway. So, when we are moving from left to right, we are going to this pathway, the arrow shows the path, where we get the corresponding T half for the up spin, and when we are coming back, that means lowering down the temperature, we have another T half due to the down spin, which is a different temperature. So, the choice between the low and high spin configuration for these molecules, what we are just telling you, that is D4, D5, D6 and D7 metal ions, which have both the two situations, that means the high spin and the low spin, is not always unique, and a spin crossover sometimes occurs. That means if we are not strictly getting a high spin D4 complex or a high spin D5 complex, we can get in same situation the low spin analogues. This may be initiated by change of pressure, temperature or light. A change of mu effective accompanies the spin crossover. So, what we are getting a diamagnetic situation to a paramagnetic situation, that means the corresponding magnetic moment will, when we will study the corresponding magnetic properties of coordination compounds, we will again come back to this particular aspect, that when we will measuring the mu effective value and there is a effect for the corresponding temperature, we should be very much careful whether we are going for a corresponding spin crossover compounds or something other thing, that means some anti-ferromagnetic interaction or ferromagnetic interaction are taking place between these two electrons occupying two different magnetic orbitals. So, if we have this particular situation for iron 2, so iron 2 compound is there, and some well known example for the dithiocarboate what we discussed earlier, for dialkylamine, so the chelate for that, this NN dithiocarbamate, and in this particular case we get this as iron 3 compound. So, these are mononegative, so charge is balanced, which is a neutral compound, and we have now for the next one, the second one, the 3D5 situation. So, these R values can be the different types of these R groups depending upon the corresponding amine. So, when R is equal to pyrrole groups or pyrrolidoyl, RRO LIDOYL, pyrrolidoyl, the mu effective, corresponding mu effective value would be equal to 5.83 mu B, 5.83 Bohr magneton. But if we change the R group from pyrrolidoyl to isobutyl, the corresponding mu effective value for the same would be 3.02 mu p. So, simply by changing the corresponding R values, we get the corresponding situation for two types of magnetic moments when we measure this at room temperature. So, at room temperature we can have these things, that means if we now see that we change the temperature. So, if we change the temperature and the magnetic moment increases with temperature. So, this magnetic moment is going from 3.02 say to 5.83 for the same substitution. These are the two situations where one is for the high spin and another is for the low spin. That means we have a crossover, and if we have a crossover region, so the high spin will be on the left hand side, which is be of the low energy, and the low spin will be on the right hand side. So, the high spin, that means this 5.83 Bohr magneton will be on the left hand side, and this 3.02 is the corresponding low spin one will be on the right hand side. So, if we increase the temperature, the magnetic moment increases. So, magnetic moment increases with temperature. That means here we are, that means we are having the low spin state. So, ground state would be the low spin state. So, we have the corresponding ground state which would be the low spin state. So, for this molecule, if we just simply plot the corresponding E values, that means the energy values E of the spin state. So, E of the low spin and E of the high spin. So, we will find there that as we change it with respect to the corresponding crystal field strength, the CF strength, so if this CF strength goes like this, and if we find that the energy for the low spin state decreasing sharply compared to the energy for the corresponding high spin state, which is not decreasing so sharply. So, these are the values for energy values for the low spin and the high spin, and this is the corresponding crossover region, and at this crossover region we have the corresponding delta value equal to P. So, as we move from here to here, just we get the corresponding value for this. So, at this region, so the corresponding available thermal energy will be in the room temperature, and we move from there, the corresponding crystal field will just give for the corresponding changeover. So, we see that one particular state will be of low energy and compared to the other state. So, the corresponding value for also can be obtained if we just see another example, which is the corresponding hydrazone derivative of pyridine 2,6 dialdehyde. which is giving rise to the corresponding complex with cobalt 2, and it's, since this ligand is a neutral one, so we have the corresponding cobalt iodide salt. So, this one having a 3d7 electronic configuration, as we all know that in this particular case also that we can have two configurations, one is the low spin, another is the high spin. So, at 80 Kelvin the value is 1.9 mu b, the magnetic moment value, and as we increase the temperature we get the corresponding value as 3.7 mu b. So, again like that of our iron example, we find the low spin state is the ground state. So, the low spin state is our ground state. So, in this particular case and in some other cases also, not only the temperature, that means if we change the temperature your situation can change from one side to the other, but also the corresponding pressure effect can also be seen, that how pressure effect can change the corresponding magnetic moment. So, when we put pressure to the corresponding compound and measure the corresponding magnetic moment, we get lower moment or lower magnetic moment, because the exerted pressure reduces the volume which can be our molar volume or the molecular volume, and as a result the Eg electrons what we can have which are directly facing the ligands, which can move the Eg electrons which are present for the corresponding high spin configuration can move to the T2G level, which is responsible for the low spin configuration, and the result is the corresponding low spin form. So, the exertion, that means when we exert pressure, there also we see that we will be able to get the corresponding low spin form from the high spin form. So, in this particular case, like the temperature, the situation is also close to the crossover region, and since the crossover region is susceptible for the change in the magnetic moment from one direction to the other, we get the corresponding spin change as well as the magnetic moment change due to the temperature as well as the pressure. So, one more example is there where we have the corresponding iron compound. This particular case we can have is a very complicated molecule though, but we have two thiocyanate coordination, and that thiocyanate coordination again give rise to the corresponding hysteresis type of loop. That means as we change the temperature, your chi-m value, this we are measuring the corresponding chi-m value like the measurement of the magnetic moment at variable temperature. So, we just go like this, again on the right hand side we move to the high spin state, and then when come down we go through some other pathway. So, we find some hysteresis loop. So, when the temperature is above Tc, the material changes from violet to white. So, there will be a color change. To erase cool the material below the Tc, there is a corresponding transition temperature which can be used for writing some material. So, these are the most latest technology, people can use it, that the skin printed with based on the corresponding spin change. The spin transition layer is deposited over there, then we have the metallic line, alumina substrate and resistive dots. So, easily implemented as the printed ink and deposited on any kind of substrate, we can go for printing such as plastic card. So, rewritable displays comprised of spin crossover copolymers bistable at room temperature. That means its stability at room temperature is different. That means in one case it will be stable in high spin and in another case it will be in the low spin state. So, some more example and some more physical characterizations for identification of the spin crossover molecules and the spin crossover situation we will see in our next class. Thank you very much.